So let's continue with our discussion on short channel effects. So we basically did channel length modulation, then we did Dibble, then we did velocity saturation, okay, and I believe we stopped with this last class, right? So we modified the equation and we got to the level 1 spice model up, right? We derived that and got all the technology parameters out, the 5 parameters, right? The level spice model is characterized by K prime, lambda, then VD sat, then VTH naught and gamma. These 5 parameters uniquely characterize the transistor in a particular technology, okay. So in this class we will move to something very critical, and it's something that has really plagued the VLSI industry because of scaling, okay, and this is called subthreshold leakage. So again, if we go back to our picture of the transistor and look at what happens when we bring the drain very close to the source, right? Now the drain that was far away was brought very close, and the drain now looks something like this, okay, n plus, this is P. My gate is now like this, okay. So if you look at this particular structure, it resembles another kind of a device, okay. This is an n plus region. This, if you consider, post the depletion and all that, because of the applied potentials, what happens is this becomes a very, very, very thin region, thin P region, okay, and therefore this structure now resembles a bipolar junction transistor, okay. So what happens is, before I actually invert the channel, there are no free electrons here, right? There are no free electrons in the channel. Before I invert, there is only excess of holes, and this side is n plus, that side is n plus, so really you can have no current flow, was the assumption. But it turns out that if you take a bipolar junction transistor that looks like this, you have an emitter, you have a very thin base, okay, emitter, base and collector, then you could have injection of electrons from this emitter to the collector through that thin base. Now this is a property of the base being very, very, very thin, okay. So what will happen is you will have some carriers that are just injected across into the base, and they sort of, by diffusion, the concentration will drop exponentially. But because the base is very thin, the concentration drop will look like a linear region, and effectively it can go through into from the base to the collector as well, right? And that's how you get bipolar junction current, by applying potentials. Here of course it happens only when there is no channel that is formed. So again, if you come back to our question of does this happen when I turn on the transistor, yes, it does happen. There is always a diffusion current, there is a drift current. It depends on which current actually dominates in that particular regime. This is not special to only the on state or the off state that I am talking about, right? So when it is off, it is this diffusion current that sort of dominates the transistor. When it is on, it is a drift current that dominates the transistor current, right? And not surprisingly, because this is like a bipolar junction transistor now, the current I off is, by the way, what was I off in our earlier model? 0, right? Now we are saying that that's not true. It is some current I naught e power VGS minus VT by n phi t into 1 minus e power minus VDS by phi t, phi capital T, into 1 plus lambda VDS, okay. This is added basically to get continuity in all, across all the regimes, that's all, right. This will not alter the actual value, okay. So the important part is that my VGS is now going to affect your leakage current exponentially, and so will your threshold voltage. So while you think that it may be good for me to actually reduce the threshold voltage of a transistor and increase the on current, remember that your off current goes up exponentially in that case. So the gain in the on current is sort of linear or quadratic at most, but the penalty in off current is exponential, right? And remember, as I told you, if this is going to happen in 8 billion transistors in your chip, then you have a serious problem, and especially if it goes up exponential, right? So what is the model of a transistor that we envisioned? We said that basically if VGS was 0 or up to a point, right? If you look at your ID versus VGS, we wanted the current to be 0 up to some point, and then it starts going up, right? So this is what we wanted, was an abrupt switch like behavior, which means that until it reaches threshold voltage, no current. The moment I exceed the threshold voltage, I am able to get a large current. Of course, large depends on whether you are talking of linear saturation, but that current is, even the linear current is quite high in any case, right? Unfortunately, this behavior is obviously not possible. You can't have such a sharp discontinuity when you are designing devices. In nature, you will never have such discontinuities, okay. So therefore, we need to see how to define this switch like behavior, okay. So what is this switch like behavior that we want? At the threshold voltage, when I lower my gate voltage slightly, I want the current to drop significantly, right? This is the behavior that I want, but I am not able to achieve it. I have non-ideality. So we are now going to define something, a particular term that will quantify this idea that we just described, okay. So that is called subthreshold slope. Yeah. 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 It is 1 minus e power minus VDS. 1 minus with VDS actually goes up. It's a RC charge up. Okay. Yeah. So first of all, if I want to look at the effect of subthreshold current, right, I can now not plot ID versus VGS, because the magnitude of the current is going to be in nanoamperes. Okay, this subthreshold equation that we wrote typically will be somewhere in nanoamps. Let me just write it, nanoamps. But obviously you just made all your calculations now, everything appears in microamps if you are talking of on current, linear current, saturation, it doesn't matter, right? Basically there is an 3 orders of magnitude difference between on current and off current. Therefore I cannot plot my I off on the linear scale and hope to analyze subthreshold leakage, right? Therefore, what do? You plot log of ID versus VGS. And it turns out that basically looks like this. Remember, on the linear scale, the same graph looked something like this. But now because we are in log, this change of 1 to 2 microamps and all is just nullified. It's basically brought down and it just looks like a very, very small change. But that's actually a very large change because I'm plotting log of ID now. Okay, I'm interested in the small changes before the current becomes very large, right? So therefore, if you look at it, at VGS equal to 0, right, I do have some off current. This is my, maybe let me call it as I of 0. The y-intercept will tell me what my log of I of 0 is. Okay, there is some non-zero current, and now what we are trying to do, somewhere here is my VT. And the hope is that if I reduce my VGS slightly below this VT, I want the current to drop significantly. Okay, so therefore first let's write down this log of ID equals log of I naught, okay, and plus, and I will say everything is log to base 10, by the way, okay, not ln, plus VGS minus VT by n phi t into log to base 10 of E, okay, plus whatever some other terms that are there. Now I will differentiate this with respect to VGS. D by d VGS of log to base 10 of ID. Everything is a constant, it all vanishes, you will get log to base 10 of E divided by n phi t. Okay. So now I am going to define my subthreshold slope S as 1 over d by d VGS of log to base 10 of ID. So this is what? N phi t by log to base 10 of E, or I can just write this as log 10 to base E into n phi t. Okay, what is n? N is the non-ideality factor. Even in the PN junction, if you remember, you have this, the applied potential. If you look at the current, it is e power V applied potential divided by n into phi t. That same non-ideality factor comes, and that is typically 1.5. For a planar device. Okay, for a FinFET, they are able to bring it down a little bit. Okay, so now we will see what the unit of this particular quantity, subthreshold slope, is, right? Top n phi t is what? What's the dimension? Volts, or I can say millivolts, right? So this is some log to base 10 of E into 1.5 into phi t is about what? At room temperature? 25 millivolt, fine. Right. Now, since I am doing a log, I am going to write this as per dk. So how much does this come out to be? Can you calculate this? Yeah? Yeah? How much? Something. So approximately it should come out to be 90 millivolt per decade. So what does this mean? It means I have to apply 90 millivolts. I have to reduce my gate voltage by 90 millivolt to drop the current by a factor of 10. Right? Ideally, I would have liked to do this with a very small value. Even 10 millivolt, I should have been able to drop this to 0, below the threshold voltage. But that's not possible. So you have some practical considerations are there, and you are limited by this 90 millivolt per decade in planar technologies. In FinFET technologies, people have been able to take this down to about 60 millivolt per decade, right? So the on-off, how good the transistor is as a switch will be determined by this particular number. Okay? Any questions here? So quite obviously, what happens now, by the way, if I plot this further here, okay, let me erase this off. What happens if I lower my VGS? Yeah? I lower VGS below 0. What will happen? Just look at that equation. So if that goes below further, what will happen? Yeah? It will decrease further, right? I keep going. What will happen? So at some point, another non-ideality kicks in, and it will cause this current to go up. Okay, you can now go and plot this. Now that you have been shown how to create schematics and do plotting and all, you can go do this and see. Plot log ID versus VGS, sweep it from minus 2 to plus 2 volt or minus 1 to plus 1 volt and see what happens. You will see this behavior. The point where this kicks in is called GIDL, gate induced drain leakage. I'll allude to this a little later, just briefly tell you what it is. But the point I'm trying to make here is that I cannot keep reducing my VGS and get reduce subthreshold leakage more and more and more and more. At some point, the drain current starts going up, not because of subthreshold leakage, but because of gate induced drain leakage. There's some weird tunneling mechanism that happens, and therefore as a designer you should be aware of this point. What is my VGS? Maybe it's minus 0.3 volt. Below minus 0.3 volt, I don't get any gain in taking my VGS any lower for subthreshold leakage. Okay, this is what you should keep in mind.